It's late. You're probably looking at a glowing monitor right now, right? Maybe a dark-themed IDE, a cup of coffee that went cold an hour ago, just sitting on your desk.
Yeah, that is the classic developer setup for sure.
Exactly. And, you are a software engineer navigating this wild, rapidly shifting landscape of artificial intelligence. And if you've been paying attention to the industry over the last, I don't know, couple of years, you've been hit over the head with one persistent message: bigger is better.
Oh, absolutely. The obsession with scale.
Right, like trillions of parameters,
Huh.
massive data centers, models so large they basically require the energy output of a small nation just to, like, tell you a joke or write a script. But tonight, we are shifting gears. Welcome to the deep dive.
It's going to be a good one.
Yeah, we are looking at a really dense set of architecture and deployment notes that completely flips that whole monolithic narrative on its head. We're talking about small language models and why scaling down rather than up might actually be the ultimate frontier for developers building real-world applications.
It's a completely necessary architectural pivot because, I mean, the sheer scale of those massive cloud-based models is incredible for generalized multi-domain reasoning.
But it's overkill, right?
Completely. As any developer listening knows, raw size just doesn't always translate to practical utility when you're actually trying to ship a lean, efficient piece of software. A trillion parameter model is a sledgehammer, and most of the time, well, you just need a scalpel.
Okay, let's unpack this. Because when we say a small language model, or SLM, we need to establish the baseline. According to the deployment notes we're looking at tonight, we are specifically talking about models with under 7 billion parameters.
Right, under 7 billion, that's the cutoff.
But the most crucial thing to establish right out of the gate is that these are not just compromised, watered-down versions of the big behemoths. Like, they aren't toys.
No, not at all. And that is the assumption you really have to break to understand the value here. The era of the massive language model was largely driven by a brute force philosophy.
Just scraping everything.
Exactly. Scrape the entire internet, feed it into a gigantic neural network, and, let sheer computational scale smooth out the inherent noise. But SLMs represent an entirely different design paradigm. The focus shifts completely away from raw parameter count and entirely onto data quality and distillation.
Yeah, and the ultimate proof of this is in our notes with the Microsoft Phi series.
Hmm.
When the first versions of Phi dropped, it was a massive wake-up call for the dev community.
It really shook things up.
Because we are talking about a model with just 3.8 billion parameters. In the AI world, that is a total lightweight. But on complex reasoning and coding benchmarks, this 3.8 billion parameter model was matching, and sometimes even beating, competitors sitting at 13 billion parameters or more.
It punched so far above its weight class.
It really did. It challenged the fundamental scaling laws that people just assumed were set in stone. So I was trying to wrap my head around how a 3.8 billion model beats a 13 billion one. Is this basically like preparing for an exam by studying one meticulously curated, perfect textbook versus trying to memorize an entire messy public library?
That is exactly it. What's fascinating here is how that curation physically changes the training process.
Yep.
I mean, the engineers didn't feed the entire unfiltered internet. They fed it what they termed textbook quality data.
Right.
In a massive uncurated data set, your public library analogy, the model has to dedicate billions of its parameters just to learn how to ignore the garbage.
Oh, wow. So it's actively wasting compute.
Yes, it spends computational power unlearning bad grammar, ignoring toxic forms, filtering out contradictory facts. During gradient descent, noisy data pulls the model's weights in conflicting directions.
That makes so much sense. It's fighting itself.
Exactly. But by curating the data to be textbook quality, highly structured, incredibly clear, logically sound, and honestly, often synthetically generated by larger models specifically for this purpose, the gradients point in a consistent direction.
So every parameter is actually doing something useful.
Every single parameter in that 3.8 billion parameter model is doing meaningful work. It just isn't carrying the dead weight of the internet's noise.
It's just pure signal. And that is a huge conceptual shift. You don't need a supercomputer to build something smart if the foundational data is just pristine.
Precisely.
Now, once you accept that you can get top-tier reasoning in a model that is under 7 billion parameters, the conversation naturally shifts from how they perform to where they can actually live. And this brings us to the developer's dream, which is on-device deployment.
Yeah, this is where it gets really practical. For the past few years, building an AI application essentially meant tethering your software to a cloud API.
Which is such a headache.
Right. You package a prompt, you send it over the network to a massive server farm, wait for the processing, and then wait for the response to travel all the way back. But an SLM is small enough to bypass that entirely.
It just sits right there.
Yep, it can load directly into the VRAM of a laptop, a smartphone, or, an edge device.
And the sources dive into the massive engineering bottlenecks this solves. Like, the most immediate one is obviously latency. Any software engineer knows the pain of an API call that hangs for 3 seconds because of like network jitter or a heavy server load.
It totally breaks the user experience.
It does. But when the model is sitting right there on the local silicon, the processing happens instantly. You get zero latency responses, which is the baseline for anything conversational or interactive.
Absolutely.
And once you solve that latency issue by running it locally, you accidentally solve an even bigger problem for enterprise apps, which is connectivity.
Which is absolutely critical for system reliability. I mean, if your application's core functionality breaks the second the user hits the cellular dead zone, it's just not a resilient architecture.
No, not at all.
By running the inference offline, the AI functions in a subway tunnel, on an airplane, or deployed out in the field on remote agricultural sensors.
And if it's offline, that means the data isn't going anywhere, right? Which solves the whole privacy nightmare. The user's prompt, their personal info, their proprietary company's source code, it never leaves the physical hardware in their hands.
That is a massive selling point.
But here's where it gets really interesting. The elimination of per token costs. For an engineer or like a startup founder, moving inference to the edge completely rewrites the financial math of building software.
Oh, completely. The cloud economics are brutal.
Yeah, when you rely on a cloud API, you pay a fraction of a cent for every token the AI reads or generates. If your app scales and goes viral, your API bill scales linearly right along with it. You could literally bankrupt yourself by succeeding.
The success penalty, they call it.
Right. But with an on-device SLM, once the app is downloaded, inference is basically free. You are utilizing the user's local compute power.
If we connect this to the bigger picture, those intertwined factors, latency, connectivity, privacy, and operating cost, they have been the primary barriers keeping AI out of the most highly regulated and critical industries in the world.
Like which ones?
Oh, think about healthcare. You cannot stream sensitive patient telemetry or diagnostic data to a third-party cloud server without triggering a massive HIPAA or SOC2 compliance audit.
Oh yeah, that's a legal minefield.
But an SLM running locally on a hospital iPad, that is a closed loop. It's entirely private. Or look at the defense sector, aerospace, high-frequency trading. In those spaces, a 200 millisecond network delay renders the data totally useless.
Wow, yeah, it has to be immediate.
By moving the intelligence directly to the edge, SLMs unlock architectural use cases that are mathematically impossible with a massive cloud dependency.
It really gives you complete sovereignty over your stack. But of course, it's a natural question any dev staring at their terminal is asking right now is, how?
Right, the implementation.
Yeah, how do you actually pack that much intelligence into a file small enough to run on a standard smartphone chip without throttling the processor into the ground? Because even at 3 billion parameters, we're still talking about a massive matrix of floating point operations.
It's still heavy math.
Exactly. And the notes we're diving into highlight a very specific, highly optimized technical toolkit.
Yeah, to deploy these models effectively on consumer hardware, engineers aren't just relying on smaller parameter counts from the start. They actually apply a stack of complementary optimization techniques post-training.
Like shrinking it down after the fact.
Exactly. The source material points to a few critical levers: pruning, quantization, knowledge distillation, and efficient architectural designs like MOE, that's mixture of experts and GQA, or group query attention.
Okay, I want to dig into quantization first, because it's often explained like lowering the resolution of an image just enough so it loads instantly but still looks sharp. But computationally, you're literally changing the math, aren't you?
You are. It's a fundamental reduction in precision.
But like you're taking high-precision 32-bit floats and squashing them down into 8-bit or even 4-bit integers. As a dev, you know that drastically reduces the VRAM needed to load the model weights into memory. That's the entire reason you can fit it on a consumer smartphone chip.
Yes, and that memory bottleneck is the crucial piece here. LLM inference is almost always memory bandwidth bound. It's not compute bound.
Wait, really? It's not the processor?
Not usually.
Yeah.
The processor is usually just sitting around waiting for the model weights to be fetched from memory. So by quantizing a 32-bit float down to a 4-bit integer, you aren't just shrinking the file size on the hard drive. You are shrinking the payload that has to travel across the memory bus for every single token generated.
So it's just physically moving less data?
Exactly. It loads instantly. And for 99% of downstream tasks, the precision loss in the weights doesn't degrade the reasoning quality in a way the end user can even detect.
That's incredible. And pruning operates on a similar physical level, right?
Yeah.
Are we essentially just packing a suitcase more efficiently? Like, you identify the neural pathways that are rarely activated or contribute very little to the output, and you just surgically cut them out. You remove the dead weight entirely.
That's a great analogy. And yes, it validates exactly what's happening. There are a few ways to handle it. But in magnitude pruning, you find the weights closest to zero and just eliminate them.
Just delete them.
Yep. In more structured pruning, you might drop entire attention heads or layers that aren't providing unique value. You're deliberately making the matrix scarcer, which just means fewer calculations per inference step.
I was also looking at the distillation and GQA stuff in the notes, and it's honestly brilliant. With grouped query attention, instead of caching every single attention key and value, which obviously eats up your device's memory as the context window grows, it groups them.
It's a huge memory saver.
Right, it shares those keys across multiple attention heads, drastically cutting down the memory footprint while keeping the model's context recall super sharp.
Because the key value cache is really the silent killer of local deployments.
Yes.
Well, as a user has a long conversation with a model, the model has to remember the context, right? Storing that context requires memory. Standard multi-head attention creates a unique key and value for every single head, which very quickly exhausts the VRAM on a local device.
It just fills up.
Exactly. Grouped query attention optimizes that memory bandwidth bottleneck, allowing these small models to handle surprisingly large context windows without crashing the host application.
Okay. And then there is knowledge distillation, which, from my understanding, isn't just a compression trick. It's a foundational part of how these SLMs are trained from day one.
It is fundamental to their performance.
You're basically using a massive 100 billion parameter model to generate millions of perfect answers, and then you train the 3 billion parameter model on those outputs.
Yeah, but the crucial mechanism there is that you aren't just training the smaller model, the student, on the final text output of the massive model, which is the teacher.
Oh, it's not just text.
No, you train it on the teacher's probability distributions, the logits. When the teacher model looks at a prompt, it assigns a probability to thousands of possible next words. By forcing the student model to mimic that entire probability distribution, it learns the nuanced reasoning pathways of the larger model.
That is so smart.
Right. It doesn't need 100 billion parameters to figure those pathways out from scratch. It is a highly efficient transfer of logic.
It's like the massive model did all the exhausting brute force research and just hands the smaller model the ultimate set of study notes.
Perfect way to put it.
And then you combine that distillation with architectural designs mentioned in our source, like MOE or mixture of experts.
MOE is highly relevant here because it separates the total parameter count from the active parameter count.
Wait, what does that mean?
Well, you might deploy a model that technically has 7 billion parameters, but it's structured as a collection of specialized subnetworks, the experts. A routing mechanism looks at the incoming token and only activates the 2 or 3 experts best suited to handle it.
Oh, wow. So they aren't all firing at once.
Exactly. For any given calculation, only a fraction of the neural network actually activates. So you get the knowledge capacity of a 7 billion parameter model, but the inference speed and compute cost of a 1 billion parameter model.
You end up with a system that is incredibly lean, blazing fast, and shockingly smart.
Yes.
And that leads us to the most practical realization for a software engineer building a system today. You don't actually have to choose between the massive cloud model and the small local model. Like, you don't have to pick a side.
You really don't. That brings us to the hybrid architecture. The source material emphasizes that for production systems, the optimal cost-quality balance isn't found in a single model, but in a multi-model orchestration.
So what does this all mean? When I was parsing through the deployment architectures, the concept of the learned router really stood out. I was thinking it's essentially acting like a medical triage nurse, right?
I love that comparison.
Yeah, like when you walk into an ER, the triage nurse instantly evaluates you. If you just have a scraped knee, they patch you up right there in the waiting room. That's the SLM. Fast, cheap, and efficient. But if you walk in with complex chest pain, they immediately route you to the specialized cardiac surgeon, which would be the massive cloud LLM.
It is a phenomenal architectural pattern. The learned router is a piece of middleware sitting between the user interface and the model layers.
Mm-hmm.
It's usually a very lightweight classifier model itself.
Okay.
Its only job is to analyze the user's incoming prompt and predict the computational complexity required to satisfy it.
But how does it actually calculate that complexity on the fly without introducing its own massive latency? I mean, you don't want the router slowing everything down.
Right, so it looks for semantic triggers
Uh-huh.
or evaluates the perplexity of the prompt. It doesn't actually generate the answer, it just assesses the difficulty. Like, summarize this email as a low-complexity task. The router flags it and sends it to the local SLM, 0 cloud token cost, 0 network latency.
Makes sense.
But refactor this 500-line Python script to use asynchronous functions and handle memory leaks. That is a high-complexity task. The router identifies the semantic markers of a complex coding request and forwards it to the massive cloud API.
And from the user's perspective, it just feels like one cohesive, incredibly fast application. Like they don't know there's a routing layer behind the scenes directing traffic.
Exactly. And from the developer's perspective, this hybrid routing system is how you build a sustainable AI business. You are reserving your expensive cloud API tokens only for the edge cases where they actually provide unique, irreplaceable value.
Yeah, you aren't paying a cloud provider a fraction of a cent just to extract a date from a text string or format a JSON payload.
It's the ultimate efficiency play.
Which is exactly what our source module is titled. So let's bring this all together. For the engineers listening, the shift towards small language models, those under 7 billion parameters, is not a step backward into budget territory. It is a massive leap forward in architectural control.
It really is.
By leveraging text-bit quality synthetic training data, developers can achieve incredible reasoning capabilities in a tiny memory footprint. By deploying directly on the user's device, you unlock 0 latency, total data privacy, offline resilience, and the end of runaway token costs.
You get your freedom back.
Yeah. And by mastering the technical toolkit quantization, pruning, distillation, and grouped query attention, you can integrate these models into a hybrid architecture where a learned router gives you the absolute optimal balance of cost and quality. It really gives you control over the chaos.
It transforms artificial intelligence from, a black box magic trick happening in a distant data center into a tangible, practical software component that you can actually engineer, optimize, and control.
But as you take back that control and start deploying these local models out in the wild, it opens up a fascinating and frankly dangerous new frontier. Because the moment your application leaves the safety of your cloud environment and hits the user's local hardware, the threat landscape fundamentally changes.
Oh, big time. You are handing the compiled intelligence directly to the client. And traditional cybersecurity perimeters just don't apply when the attacker has physical access to the weights.
So here is a thought to leave you with tonight as you stare at that IDE. Now that you know how to build and deploy this highly efficient hybrid intelligence, how are you going to protect it?
That's the real question.
When the SLM is running locally on a device, what stops a malicious actor with infinite time from reverse engineering the model extraction? How do you build a defense-in-depth strategy when your system is vulnerable to local prompt injections that trick your learned routing logic into bypassing security filters? Or data poisoning that corrupts the very textbook quality fine-tuning you rely on?
It's a whole new paradigm of risk.
It is. The efficiency play solves the cost and the latency, but it introduces a whole new world of adversarial vulnerabilities at the edge. That is the next great engineering challenge waiting for you to solve. Thanks for joining us for this deep dive. We'll catch you next time.